All right, folks, it's AP Calculus, okay, back with another lesson here. Mr. Berto will be talking about slope fields, okay, day 2. That's what's going on with this lesson right here. Hopefully you're able to download the things you need to from the website. Hopefully you have printers. If not, do the best you can with writing things down. But, you know, yesterday we talked about slope fields, okay, and really it's just a model for a general solution, okay? It represents infinitely many particular solutions. Try to remember about dependence, okay? If your derivative is dependent upon x only, when you draw out your slope field, you'll see that in a vertical line, you have the exact same slopes, okay? Because it's not dependent upon y. We don't care about y what is. So when you switch to, from one y value to another y value, it doesn't change the slope. But when you change from one x value to another x value, it does. So same slopes in a vertical line, dependent upon x. Same slopes in a horizontal line, dependent upon y. If you don't have the same slopes in a vertical or horizontal line, that means you're dependent upon x and y, okay? And that's going to help you. You know, this ditto right here, if you actually turn the page, magically it's going to go from number 3 to number 5, okay? What happened to number 4? Where's number 4? Nobody cares. Anyway, so here, you know, let's actually talk about slope fields day 2. Now we're not creating the slope fields, we're being given the slope fields, and then we have to determine which differential equation represents the slope field. So that's what we're really doing here. Slope fields day 2. Slope fields day 2. So I think that's really just 1.2 day 2, something like that. Okay, and you know, some people are like, I'll solve each differential equation, get a general solution, then see which general solution is modeled here. That's bad for so many different reasons. First off, solving every single one of these is going to take you forever. And even afterward, it's not easy to look at it and be like, you know, what the heck does this thing actually represent? I mean, you know, here, well, we didn't solve it yesterday, but you get something, it wouldn't be so easy to understand that you get a graph like this, as opposed to this situation, which is much easier. Rarely does it go that way. I mean, sometimes they actually give you y equals and ask which one represents a slope field for it, you know, a collection of tangent lines, pieces of tangent lines, but you won't really see something like that usually. Anyway, pieces of tangent lines, because if you just drew the whole tangent lines, these things would go on forever. It'd look like a complete mess. This is an intense slope field right here. There are a lot of different things you could do to narrow it down. Try to think about dependence first. You could see that if you look here, maybe pick this x value. You know, if you just keep moving in a vertical line, look what happens to these slopes. These slopes change, okay, as you move in a vertical line. So that means that this thing right here is actually going to be dependent, you know, at least on y. It's, you know, as far as x is concerned, if you move in a horizontal line, you'll see that the slopes, they do not change, okay? They remain the same, okay? And if you actually have the same slope in a horizontal line, that means that you're dependent, okay, on y, okay? So dependent on y. You know, why are we dependent upon y? Because if you move horizontally, you're changing x, but the slope isn't changing, so who cares about x? If you move vertically, you're changing y, and the slope is changing. That's why we depend on y. Why is that important? This thing depends on y only. Depends on y only. So in part A over here, they're saying the derivative of the slope depends on x and y. I don't think so. Part B, they're saying it depends on x only. No. C is a possibility. That's y only. But D is no good. And E is also a possibility. So right there, you've already narrowed it down. You can't always do that because a lot of times you look in a horizontal line or a vertical line, you'll see the slopes are different for both. So it's dependent upon x and y. But this can really help you out. The next thing I check for is slopes of 0 because they're easy to recognize. You know, if you look over here, you're like, well, it's a positive slope, but you don't know what the heck it is. But here you could see these horizontal tangent lines in a horizontal line here. We know the slope is equal to 0 when y is equal to -1. You know, if y is equal to -1, you could see it generates a slope of 0 every single time. If you plug -1 into C for y, -1 plus 1 gives you 0. We want that. You know, over here with E, if you plug in y equals -1, -1 minus 1 is going to give you -2. There's not a slope of -2 at the places where y is equal to 1. If there was a slope of -2, it'd look more like this right here. That's not true, okay? So that's why we know that C is the answer. You know, you should always try to do dependence at first. Then you could try to actually check slopes of 0. Then you could do something known as the quadrant game, which we'll talk about in a second. But one of the best ways to do it is to just pick a point, okay? Like if you pick a point, and you might have to pick several points, but this point right here, you can see is the point 1, 0. So if x is 1, y is 0, you should end up with a positive slope. So if x is 1, y is 0, we don't care about x here. But if y is 0, 0 plus 1 is going to be positive 1. Kind of looks like that could be a slope of positive 1. Over here, if you plug in the 0, 0 minus 1 is negative 1, not a slope of negative 1. So believe it or not, the best way to figure out which differential equation corresponds to a given slope field is to just pick points, plug them in, and see if you get slopes that match up. But that can be a little prolonged, okay, and take a lot of time sometimes. So try to think about dependence and where slopes are equal to 0. Like if you take a look at number 6, I don't think there's any dependence here. Maybe there is dependence. Let's see. I think there actually is dependence. If you walk in a horizontal line, you can see the slopes are changing. Okay, so the slopes have to be dependent upon x, okay, somewhat. If x changes, the slopes change. But you can see in a horizontal line, okay, if you move in a horizontal line, the slopes are not changing. They're staying exactly the same. And that means we're dependent upon x, dependent upon y, what was I saying? Dependent upon x only, okay? So this one right here is dependent on x, okay? So remember, same slope in a vertical line, you're dependent upon x. Same slope in a horizontal line, dependent upon y. Once again, look in a vertical line, the slopes are the same. So if you change y, it doesn't make a difference. Look in a horizontal line, the slopes are different. So if you change x, it does make a difference. So we depend on x here. So we could wipe out A. B is good, dependent upon x. Remember, it's dependent upon x only. If it's dependent upon x and y, you're going to see that the slopes are going to change in a vertical and horizontal line. So look, B is in the game, C is in the game, D is in the game, and E is in the game as well. Okay, so we got a lot of ones here that are dependent upon x only. You could go for 0 slopes next. You could see that you have slopes of 0. And remember, we're dependent upon x here, so we really care about what x equals. You can see when x is equal to 0, you always get a slope of 0. So if you plug in 0 to these derivatives down here for x, you have to get a 0 back, which happens in B, right? You square 0, you get a 0, but not in C. If you plug in a 0, you get a negative 4. So, if I plug in this point right here, where x is 0 and y is 1, 2, 3, 4, 5, 6, negative 7, who cares about y, by the way, because there's no y to plug into. But if I plug in x equals 0 here, I get a negative 4 back. There's supposed to be a dot right here. You can see if there's a slope of negative 4, it would look something like this, okay? It wouldn't look like a horizontal line. That's why that guy's no good. Same thing with D, right? If x is 0, the slope is equal to 4, not 0. Problem is E is also still in the running. Okay, you can see with E right here that if, x is equal to 0, the slope is still equal to 0. But we've narrowed it down. Now you can do something known as the quadrant game. The quadrant game isn't as powerful as plugging in points. You might just want to pick a point at this point and actually plug in and see what kind of slope you get back. But the thing with the quadrant game is if you look in each quadrant and the slopes are either all positive or are negative, you could use the quadrant game. Look in the first quadrant, you can see all the slopes are positive. In the second quadrant, all the slopes are positive. In the third quadrant, this is the fourth quadrant, sorry. In the second quadrant, all slopes are negative. And the third quadrant, all slopes are negative. So if there's no changing of positive or negative slopes in each quadrant, you could think about the quadrant game. The quadrant game means if you plot a point in each quadrant, first quadrant point has to have a positive x coordinate, a positive y coordinate. Second quadrant point has a negative y coordinate, has a negative x coordinate and a positive y coordinate, right? Because you got to move left and then move up. In the third quadrant, both coordinates are negative. You got to move to the left and move downward. And in the fourth quadrant, you have a positive x coordinate and a negative y coordinate. Remember, we only care about the x coordinates here, but you can see in the first quadrant, all x coordinates are positive. All slopes are positive. So if I plug in a positive number for x, I have to get a positive slope back. You do for both of these. You square a positive, you get a positive back. You multiply a positive by 1/2, you get a positive back. But you'll see it starts changing in the second quadrant. Second quadrant, the slopes are negative, and you can see that x has to be negative. If you plug in a negative to x squared, you don't get a negative back. You square a negative, you get a positive back. Take a negative and square it, you get a positive, and you do not have positive slopes in the second quadrant. So this cannot be the appropriate differential equation. You're supposed to get positive slopes back. But if you take a negative number and multiply it by 1/2, you will get a negative back. You'll get negative slopes. So that works right there. That's a quadrant game. You don't have to use the quadrant game. You could just pick a point. I mean, they don't really have the tick marks to indicate points here. Usually they do on the AP. I don't know, maybe this point was this right here, the point -1, 1. All right, so negative 1, comma 1. You can see x is negative, y is positive. So plug in x equal to negative 1, you got to get a negative slope back, right? But if x is equal to negative 1 here, you get a positive 1 back. It's not a slope of positive 1. That's a slope of negative 1, or it's a slope of something negative. It's actually negative 1/2, right? Because if you plug in a negative 1 right here, 1/2 times negative 1 gives you negative 1/2. Looks like that could be a slope of negative 1/2. So look, start with dependence. If it helps you, great. Move on to second, I would suggest slopes of 0 because they're really easy to take a look at real quick. Third and lastly, you could go for the quadrant game, which won't always work. Sometimes in each quadrant, slopes are changing from positive to negative, but you can always plot a point. It's probably the best way to do it. So these problems, they're not so easy. They're tricky, but they're really not that bad if you think about plotting points. If you have a nice diagram. On the AP, you'll have a nice diagram. These are horrible diagrams right here, okay? This was a recent topic many years ago. 20 years ago, it was a recent topic. It was hard to get problems for them. Now there's a lot of other problems. I should probably remove this page, but it still has its, advantages. And it's really just a printout of a graphing calculator. And I kid you not, for years, this is the stupidity of your AP calculus teacher. I thought it was a Spanish graphing calculator. Spanish graphing calculator, why? You see the word zoom here, you see the word main. But I saw this and I was like, oh, Degato. So for some reason, I thought that was like a Spanish word. I kid you not, it took me, I don't know, 10, 12, 13, maybe 14 or 15 years to realize that just represents degree auto. All right, so when you think about your struggles in calculus, think about the fact that, your teacher can sometimes be a complete idiot. I think I'm going to sneeze. Oh, no, it's going away. Oh, it's coming back. Nope, going. If you don't say bless you, what's wrong with you? And besides, I just eviscerated myself, calling myself an idiot. Connor Crowley's probably having like a party at home or something like that. And Brennan Finnegan's just sitting there laughing. All right, so anyway, match the slope fields to the given differential equation. Also, I'm sure Kayla Allers and her best friend Devin Warren are probably just looking at each other with faces right now like, can you just end this video? Just kidding. So anyway, here you might realize that how we going to do this, if we look at each of these, okay, over here, let's go for the slope field first. Why not? This slope field, think about dependence right here. Same slopes in a horizontal line, different slopes in a vertical line. So same slopes in a horizontal line. That means you're dependent upon y. So really, it's going to be, how about this? The derivative is going to be a function of y. Let's put it that way. So it's got to be one of the ones with only a y in it. It's got to be a or b. Quadrant game works out nicely here because you can see all the slopes in the first quadrant are negative. In the first quadrant, y is positive. So you need to, with a positive y, generate a negative slope. That happens with b right here. If you negate a positive, it becomes negative. That's why this guy right here is going to be b. All right, so something to think about. Here in the second one, you can see, do we have dependence? Well, if you check in a horizontal line, the slopes are changing, okay? So it's not dependent upon y right there. But if you check in a vertical line, the slopes are staying the same, okay? And that means it's dependent upon x only. So our derivative right here is going to be a function of x. Sorry, I have some cold symptoms here. I was sick last week. I don't know if it was coronavirus or not. I hope it was because I'm kind of over it right now. So I have antibodies, but I guess we'll see what we can see. So anyway, same slope in a vertical line. You know that you're actually dependent upon x because who cares if y changes, but you care if x changes. So that means I'm looking about in the ones only dependent upon x. And the quadrant game, once again, first quadrant, x is positive. And the slopes are all positive. So you want to take a positive x, plug it into the derivative in terms of x, get a positive back. That's going to be d right here, okay? Moving on, this guy right here, we can see same slopes, not in a horizontal line, but you got the same slopes in a vertical line. Remember, same slopes in a vertical line, you're dependent upon x. All right, so that one right there, the derivative is going to be a function of x. So it has to be c right here. And it makes sense. The first quadrant, x values are positive, but the slopes are negative. So you want to negate those positive x values to actually end up with those negative slopes. This guy right here, the fourth one, you can see we have the same slopes in a horizontal line. Okay, so that means we're dependent upon y. So derivative is a function of y. The only one here, the left, that's a function of y is going to be a. Once again, quadrant game, first quadrant, all the y values are positive, all the slopes are positive, so the y values being positive will generate a positive slope. Process of elimination means we know this guy is e, and you'll see You don't have the same slope in a horizontal line. You don't have the same slope in a vertical line. So this derivative is dependent upon x and y, which is why it's got to be e right here. But just something that's really cute, because you can't use the quadrant game, right? You can see in the first quadrant, you got positive slopes, you got negative slopes. You could try to pick points, okay? And if you actually pick points here, you might notice that this slope of 0 kind of occurs exactly at the line y equals x, right? So apparently when y equals x, you have a slope of 0, which would be true if the slope was represented by x minus y. So something that's kind of cute there. You know, sometimes you got to think about these problems a little bit. Other times you can kind of, you know, act a little bit on instinct. You know, last 3 problems right here, we're into the stretch run. I'll check for dependence first. You can see if you go in a horizontal line, slopes differ. If you go in a vertical line, slopes differ. So we're dependent upon x and y. So that means you better see an x and a y in a derivative. If you don't, knock them out, like e over here. I don't know if you can see anything I was just showing right there. Horizontal line, the slopes differ. Vertical line, the slopes differ. That's why we're dependent upon x and y. And e is dependent only on y, so we can get rid of e. Be quiet. Maybe slope of 0. You know, look, you could see that right here on the x-axis, when y is equal to 0, you have a slope of 0. That's how they show those horizontal tangent lines on the x-axis. They kind of break it up that way. Slope equals 0 when y equals 0, which means you could wipe out a, because a, when y is equal to 0, the slope would be undefined, right? You'd be dividing by 0. B, if y is equal to 0, you can see 0 divided by something could equal 0, so that's a possibility. C is no good, because if y was equal to 0, slope would be non-existent. Never really show it on the AP exam. It looks like these slopes are tending toward a vertical line right here from the left and from the right of the origin. So probably when y equals 0, you are undefined. When x equals 0, pardon me, you are undefined, okay, which would make sense, the slope, because that's what would happen in B and D, because if x is 0, you'd be undefined right there. But anyway, you can go quadrant game or pick a point. Maybe we pick a point, right? Maybe we pick the point, I don't know, 1, 2, 3, comma, negative 2, right? So the point 3, comma, negative 2 right here. And if I plug in the point 3, comma, negative 2 to the derivative, I better get a positive slope back, okay? And if you plug 3, comma, negative 2 into this guy right here, you negate the negative 2 up top, 3 downstairs, you get 2/3, okay? That's a positive slope, and that makes sense, okay? We want a positive slope right there. Let's see what happens if we plug in here. If you plug in y is negative 2 and x is 3, you get a negative slope, okay? And that is not a negative slope. Hence, I know that B is my answer. You could have gone quadrant game here. Quadrant game works quite well, but really plugging in a point, it's just like you're doing the quadrant game just for one specific point. The problem is sometimes you pick a point and, you know, several of your answers are going to indicate either the positive or the negative slope you're looking for. You have to go to different quadrants and pick points from different quadrants to get your result there. You know, looking at number 9, do we have dependence? Even 9 and 10, you could pause right now, do them, okay, and then come back and then we'll talk about them. And we're back. You know, you could see that we have the same slopes in a horizontal line, different slopes in a vertical line. So we're dependent on y. Okay, so if you move vertically and you change slope, that means y is changing. So you're depending on y. If you move horizontally, you don't change slope, you're changing x. But who cares? Because you're not changing slope. Dependent upon y only, knock down a. Get out of here, brother. Knock out d as well, right? They're only dependent upon x. Now dependent upon y, slope of 0. I can see right here, okay, at the x-axis, slope is 0 when y equals 0. Okay, you can see that B, if y is equal to 0, you get a 0 back. But C, if y equals 0, you get 1 over 0 back, which is undefined. So you'd have vertical lines right there, or some other possibility that we don't really talk about in here. And E works as well, right? If y is 0, negative 0 is still 0. So maybe pick a point. Let's go second quadrant this time. Pick the point 1, 2, 1, 2, 3. So negative 2, comma 3. Okay, and you can see that the slope is negative. So when I plug in that, it's really only the 3 I worry about, right? Because we're only dependent upon y. I want a negative slope. Plug in a 3 here, you get a 3 back. This is a positive slope. This is not a positive slope. Plug in a 3 here, you get a negative 3 back. And it looks like this could be a slope of negative 3. At least it's a negative, okay? So that's how we get our answer of E right there. So these problems aren't so easy, but they're not as bad as you might think. And I didn't even start talking about the dependence thing until really last year I focused on it. I think it's really helpful, but for some problems it won't help, like number 10. You can see that in a horizontal line, the slopes differ. In a vertical line, the slopes differ. That means you're dependent on x and y. And I said it doesn't help, but it actually does with eliminating answers because B is not dependent upon x and y, and neither is E, okay? They're only dependent upon one or the other, so we can knock them out. Slope of 0, I see slopes of 0 right here when, x is equal to 0. So our slope equal to 0 when x equals 0, which works for all these, unfortunately. You know, x, 0 times a number could still be 0. 0 divided by a number, or negative 0 divided by a number, could still be equal to 0. So that doesn't really help you out, okay? It might be time to go quadrant game here, or pick a point, maybe a first quadrant point this time, maybe the point 2, comma 2. All right, so this right here is my point 2, comma 2. And when x is 2 and y is 2, you better get a negative answer back. It doesn't happen in part A, right? 2 times 2 would be 4. That's not negative. It doesn't happen in C either. 2 divided by 2 would be 1. That's not negative. But in part D over here, that gives you negative 2 divided by 2, which is negative 1. And that could foreseeably be a slope of negative 1. Regardless, at least, it's negative, okay? So, you know, once again, identifying a slope field, given a slope field, identifying which differential equation corresponds to it. That's essentially what we did today. Check for dependence first. Same slope, okay, in a horizontal line dependent upon y. Same slope in a vertical line dependent upon x. After that, I check for slopes of 0 because it can get you to an answer quickly sometimes. Really, the best way is to plug in that point. You just might have to plug in more than one point. And sometimes you kind of got to think about it. You know, some of the homework problems tonight, not so easy, but do the best you can, okay? You probably won't see these on your AP because they're really predominantly part 1 types of questions, but who knows what they're going to do as far as the AP is concerned. I think I was telling you I'd have more information about the AP on Wednesday, which was yesterday, right? This is Thursday's video. I'm an idiot, okay, because they said it would be April 3rd when there's more information. I don't know. For some reason, I just thought April 3rd was Wednesday. Just losing my mind in my quarantine here. How many old Sega Genesis games can you play over and over? The answer, a lot. Anyway, it's on Friday, okay? So tomorrow they're going to come out with more information about your AP exam. Don't be discouraged, okay? I'm telling you, you could really still do well on this thing, okay? We'll talk about trying to predict some questions and stuff like that. But, you know, I'm going to do my review like normal, okay? Because you need to know stuff like this for next year, okay? That's what this class is about, not just the advanced placement exam. We'll try to predict some questions. We'll talk about what you won't see on your AP, but we're going to review all of it, okay? But we'll try to, you know, focus more on the things that are going to for certainly, you know, be on your AP exam, or at least certainly could be on your AP exam. Anyway, you know, tomorrow we talk about exponential growth and decay, which is a differential equation, extraordinarily apt as far as the coronavirus is concerned. Something to talk about with the coronavirus right here. You can turn off the video right now if you want to, but this is so cool, okay? They're talking about this apex, right? Flattening this curve, okay? So that when we get to the maximum, math word right there, of, you know, the amount of infections, we can keep it down to a certain level that the healthcare system can handle. And I've heard about them say over and over the fact that the infections in New York right now, they're still increasing, but the rate at which they were increasing is actually getting smaller. That's concavity, okay? You can see here that first, I didn't really draw this perfectly. I'll do it again. You know, first when this thing increases, it increases looking like a U, concave up, but then it increases looking like an N, concave down. And right here, where it changes from a U to an N, that's the inflection point. You know, see right now, from here to here, the cases of coronavirus are increasing, but the rate is also increasing, okay? This thing is getting more and more steep. It's concave up. From here to here, okay, you can see that the amount of cases is increasing, but the rate at which they're increasing is getting smaller, okay? That means it's concave down, okay? And that's really what's going on. We're around here, okay? Hopefully we get to that apex as soon as possible and we get it as low as possible. And then after that, we can handle things, okay? But, you know, math in a real-world situation right there for concavity. Tomorrow we talk about exponential growth and decay, obviously relates to this virus as well. So anyway, some cool real-world math stuff right there. Anyway, that's Thursday's video. So here's Berto once again signing out. See you later, y'all.